Okay, thank you for this invitation to this conference. The title of my presentation, our presentation is, as you said, an approach CPS, cyber physical systems for the smart monitoring of industrial systems. The work has been done by Nesrine, Jlassi, and supervised by all of us, me, my colleague Cédrick, Béler, and another colleague, Omar, Khlaief. We are from, the work has been done within the laboratory, which is called Production Engineering Laboratory, which is in École Nationale d'Ingénieurs de Tarbes. It's National School of Engineering in Tarbes, southwest of France. And we work within then we work within the field which is called Prognostics and Health Management. But before presenting this, here is the motivation of the work. We work on this field, which is PHM and predictive maintenance. And as you see, the industrial revolutions started from the first to now we are in the fourth revolution, which is Industry 4.0. And within this new industry, we have different technologies, among which we have CPS, cyber physical systems, and also PHM, which is prognostics and health management. And also what we work in this, what we have done in this work is related to predictive maintenance. So before presenting this PHM, predictive maintenance, and also CPS and IoT, how we applied them on industrial systems, here are just some introductions for system monitoring. Here we aim at putting or placing sensors on the system, industrial system, physical system, and these sensors provide us data, information about the dynamics of the system, its failures, also abnormal situations, and then we track this operation of the system in time. And then by analyzing the data, we can observe what happens on the system. And then also, if there are any failures, particularly we are working on failures, we can detect them, diagnose them. Sometimes also we can prognose them, and then take appropriate decisions by doing control actions, for example, on the system online to keep it safe for the operators and the environment. Within this, system monitoring, it's within a biggest framework, which is prognostics and health management. We call it the acronym PHM. And in this PHM paradigm, we have different steps. You have below the system, which can be physical, like, for example, here I presented just a smart grid. Of course, it can be a CPS, cyber physical system. And then with this system, we have several components. These components or systems or subsystems may fail, can have abnormal situations. And then, as I said, we try to monitor this system by through sensors and also other data we can collect on it. So we have first to collect representative data. That means we cannot use any data. The data should represent the behavior of the system, either functional or dysfunctional behavior. And then, based on this data collected, with the first pre-processing, that means we first do filtering, smoothing, data completeness, verification, remove outliers. We can also do sometimes normalizations, because when we have several sensors, we don't have the same values, amplitude, magnitudes. So all these steps, we call them data pre-processing. This step is to be sure that the data are reliable. And then once we have this data which are reliable, we do data processing. That means we look at the data which are raw initially, and then we try to extract features, select the best ones of these features, Also, we can reduce the number of features. Sometimes we can extract more than 100 features only for one signal or some signals. And then we have to reduce this number of features. And then by doing all these steps, feature extraction, selection, and reduction, we can also build health indicators. We call health indicators. That means they are signals which allow us to track the behavior of the system in time. And then by doing this, we can online and step by step at each moment estimate the health state of the system, if it's okay or not okay. If there is an abnormal situation of the system, then we can go to diagnose the cause of this anomaly. And then sometimes we need, if the failure is progressive or incipient failure, we can do failure prognostics. That means we try to estimate or predict what we call remaining useful life about the system, of course, within confidence intervals, because when we do predictions, we have uncertainties on the predictions. And then based on all this information, we can take decisions, propose decisions, and behind the decisions, make actions on the system to keep it safe. Sometimes we can do reconfigurations, we can do tolerant control, fault control, we can do also, work on the redesign of the system and so on. And behind now this PHM paradigm, behind each step, we have algorithms which we develop, and these algorithms and the information which are given by the outputs of these algorithms are used to do what we call predictive maintenance. That means we do maintenance based on the predictions. Here you have some definitions. You are aware about them. IoT, you know what is it, Internet of Things. M2M is what we call machine to machine. They are when you have machines communicating between them and also between the humans. We have also wireless sensor networks, which are the sensors which are connected each other. So what are CPS? They are systems integrating electronics and software, sensors and actuators with communication capabilities. They have the main basic functions. We can detect features of the physical system. We can compute and process appropriately from sensor input and other data sources, and generate responses or response actions through actuations. If you see at the pictures, you have a physical system. We have the sensors which monitor the system, and then based on these sensors, we can also connect to digital twin, and by communicating between the physical and the virtual systems, we can act on the physical system to correct it and keep it in good operating conditions. We can also speak about system of systems. That means we have a system containing other systems, and then how to work to communicate between all these systems to reach a main goal or main goals. We call this system of systems. We have also CPS OS, that means cyber physical systems of systems or system of systems. They are cyber physical systems that represent the characteristics of system of system. That means you have not only one system, you have many systems connected, and also you have cyber things which are and physical things which are connected between them. You have here a summary of all these definitions and the link between them. The IoT can contain all these paradigms. You have cyber physical systems. You have the virtual and the physical modes. You have the wireless sensor networks. You have the machine-to-machine, etc. And all this can be within the Internet of Things. So what is the problematic we tackled during the work of Nesrine? It was how can a cyber physical system and the Internet of Things guide the monitoring and detection of failures in industrial systems. How we can merge both CPS and Internet of Things to do monitoring of these systems. So you have in literature different architectures which were proposed, like IoT, machine to machine, and you have also one architecture which is called 5C, which was proposed by Jlassi, which is dedicated for cyber physical systems. You have here the main ones, and you can find them in the reference number 2 and other references. We have also another architecture for intelligent monitoring. So you have a system which is controlled with actuators. You have a system which is controlled. And to be controlled, you need sensors, of course. And then we have some set points here in the left. We compare the set points with the feedback given by the sensors, and then we act on the system to keep it. Okay? So you have here the physical world, which is the system with the sensors and also sometimes with the actuators. And then you have virtual world. They are all the control algorithms, monitoring algorithms, management algorithms, all things we can do by algorithms. And both worlds communicate, of course, to have both virtual and physical communication or link. You have also another architecture here. You have the physical world in the left. And if you see here, you have the physical system with its sensors. You have the actuators, of course. We have also sometimes manual interventions. That means that the human can interact with the system to change some parameters, for example. And then all this can be shown or sent to a virtual interface where we have the algorithms and also the management, the display interfaces, and so on. So in our case, we have worked on an architecture to monitor intelligently, smartly the physical systems. The main objective is to demonstrate the application of cyber physical systems to system monitoring. Develop an interface for monitoring, detection, and decision support of a wind farm via wireless network. All this connecting the wind farm to the network provides the ability to access and control data in real time from anywhere. So we wanted to monitor these systems remotely and also act on them remotely. So the benefit is to remotely supervise the wind turbine, which can be also a farm of wind turbines. Remote management of parameters. We can act remotely on the system. We can visualize all the production data, monitoring data. We can exchange the data from the sensors to the human interface. Okay, but also we have some drawbacks. We have pseudo real time because we don't have powerful real-time applications or hardware. Availability offline mode and degraded mode, we cannot have them on time. And also we have security issues. That means the system can be hacked because we have not implemented very secured algorithms. So here you have the prototyping of our architecture proposed by Nesrine. So you have the physical system here with the sensors, current sensors, temperature sensors, position sensors, and so on. And the physical system, they were wind turbines, not only one, but many. You have here the base node with data acquisition system, which is an Arduino card. We have a client or server, and all with the network, and then we can exchange to store the data. We have here the prototyping, the network, the basic node, we have microcontrollers. with sensors and actuators. Local also storage we can have. The full node, we have microcomputer, operating system, and the programs or the algorithms to display the data and to acquire, to store, and run all the applications. You have all the components here. Here you have an overview of the architecture, which was implemented by Nesrine during her master internship. You have the wind turbines here. She used 3. You have here an anemometer, sorry, to measure the wind speed. We have the rotor here to exchange, and you have Raspberry Pi, which is a mini computer, which she used. Here you have a set of sensors she used. You have accelerometers. You have all low power, sorry, you have here the ESP32 for exchanges. You have bending sensor here. You have this component to control small motors in low voltage, and this one mainly for to control the speed of the wind turbines. You have current sensor here, proximity and light sensor, and you have temperature sensor and pressure sensor here. She implemented all, as you see on this card, just as a proof of concept. And here is the client mode. All what she implemented, we can see here the programs, and we can get the data. For example, you have here the pressure, okay, at that time, and all the coding and the program implementation she made. Here you have the server mode, how it was implemented. So you can see here the reference of the server, the address of the server. And she proposed also a user interface with here on off of winds, okay, individually or only set of them or all of them. She could monitor the temperature, the power, the wind speed, the wind direction, and the rotation of the wind turbines. And also she could see the weather at that time. So the user interface, we can see all these elements, as I said. You have them here. And during the monitoring, she made some scenarios. For example, 4 scenarios: high speed, bad efficiency, phase failure, and network failure. For the high speed, if the speed is too much, it can cause the turbine to rotate uncontrollably, and this is not good. So we can act on the speed and make it reasonable to make the wind turbine safe. The bad efficiency, the speed increases, the current continues to be produced, but there is a loss of efficiency. So an alert is therefore sent to warn the operator of a pending malfunction, malfunction. We have in the phase failure, electricity production stops, the system breaks down, so we can monitor this. And the last scenario for network failure, communication becomes impossible between the sensors and the interface. There is no more interface, nor parameters to monitor. We cannot see the parameters monitored on the wind turbines. To conclude, the IoT for system monitor overcomes several challenges. It's pretty fantastic opportunity to improve and optimize production tools, improve the performance of the industry, respect the environment issues, especially in terms of energy consumption, we can control remotely, and avoid malfunctions, anomalies. But we have also to look on some drawbacks like availability of this IoT. They are pseudo real-time, and also about the security when communicating, because they can be hacked. So to avoid all this, we have to work on this in future works. Here you have some references presented in this work, and thank you. I arrived at the end of the presentation. Thank you for your attention. If you have questions, please don't hesitate.
Thank you, Professor. Thank you very much for your great presentation. Does anyone have any question? Are there any questions from forum? Professor, if you don't mind, can you mention, is there any limitation in it in the work?
Yes, the limitations, we have many indeed. If we see at the end, what we have here is that because we worked on IoT, this IoT, of course, we can use them to monitor the systems, okay? We can use them to monitor the systems, but we have, as they are remote, the first issue is security. So we have to work on this. The second is some of them are not reliable, because if here we have applied them on a very small application, which was a lab application. You see these wind turbines, they are very small, and we can put them on a table. But if we are in industry, the sensors should be very reliable to be used. Otherwise, the industrials, they will not accept them. And until now, we don't have, not all of the sensors are accepted by industrials. So this is another limitation. The other limitation is if we have many IoT which are placed on the system, then we will have a lot of data, big data. And then the problem is how to process, handle all this data, and also how to be sure that about the main useful ones among these data. Because it's not putting the sensors, sometimes it's not a problem, but if a sensor is not reliable or is not useful, it's loss of money. So we have to work on all these limitations. And the last one is how now to exploit this data provided by the IoT to really predict what we call a remaining useful life of the systems. That means how to predict if the failure will be there on the system. It's not only to detect, but to predict the remaining useful life, how much time it remains for the system to be shut down or failed. This is very challenging. We are working on it.